I am Kimcarl Cacas and I will be reporting about special diodes. So first is the Schottky diode, and Schottky diodes are constructed of a metal to N junction rather than a PN semiconductor junction. Also known as hot carrier diodes, Schottky diodes are fast switching times, low reverse recovery time, low forward voltage drop, typically volts for a metal silicon junction, and low junction capacitance. So here is the um, schematic symbol. Regardless of switching speed, the 0.7 volts forward voltage drop of silicon diodes causes poor efficiency and low voltage supplies. This is not a problem in say 10 volt supply in a 1 volt supply. The 0.7 volt drop is a substantial portion of the output. One solution is to use a Schottky power diode which has a lower forward drop. So here is the next one, tunnel diode. As the voltage is increased, the current increases and reaches a peak value called current, or IP, I sub P. If the voltage is increased a little more, the current actually begins to reach a low point called the valley current, or IV. If the voltage is increased further, begins to increase again, this time without decreasing into another valley. So, the forward voltages, this anyway is the schematic symbol. The forward voltages necessary to drive a tunnel diode to its peak and valley currents are known as peak voltage, or VP, and valley voltage, VV, respectively. The region on the graph where the current is decreasing while applied voltage is increasing between VP and VV on the horizontal scale is known as the region of negative resistance. So next is the light emitting diode. So we all know the LED, the abbreviation. Electrons flowing through a PN junction experience similar transitions in energy level and emit radiant energy as they do so. The frequency of this radiant energy is determined by the crystal structure of the semiconductor material and the elements comprising it. Some semiconductor junctions, composed of special chemical combinations, emit radiant energy within the spectrum of visible light as the electrons change energy levels. So this is the schematic symbol for the light emitting diode. So next is the laser diodes, or actually laser is an abbreviation for light amplification by stimulated emission of radiation. Some laser diodes require special high-power pulsing circuits to deliver large quantities of voltage and current in short bursts. Other laser diodes may be operated continuously at a lower power. In the continuous laser action occurs only within a certain range of diode current, necessitating some form of current regulator circuit. As laser diodes age, their power requirements may change. But it should be remembered that low-power laser diodes like LEDs are fairly long-lived devices, with typical service lives in the tens of thousands of hours. So next is the photodiodes. It is a diode optimized to produce an electron current flow in response to irradiation by ultraviolet, visible, or infrared light. Silicon is most often used to fabricate photodiodes, though germanium and gallium arsenide can be used. The junction through which light enters the semiconductor must be thin enough to pass most of the light on the active region, or depletion region, where light is converted to electron-hole pairs. So in the figure below, this is the schematic symbol. A shallow P-type diffusion into an N-type water produces a PN junction near the surface of the water. The p-type layer needs to be thin to pass as much light as possible. A heavy N+ diffusion on the back of the wafer makes contact with metallization. The top metallization may be a fine grid of metallic fingers on the top of the water for large cells wafer. In small photodiodes, the top contact might be a sole bond wire contacting the bare p-type silicon top. So, next is the varicap or the varactor diode. If a diode is reverse biased, an insulating depletion region forms between the two semiconductive layers. In many diodes, the width of the depletion region may be changed by varying the reverse bias. This varies the capacitance. This effect is accentuated in varicap diodes. So, if a varicap diode is a part of resonant circuit, as in the figure here, the frequency may be varied with a control voltage or V sub-control. A large capacitance, low X sub C, in series with the varicap prevents V controlled from being shorted out by inductor L. As long as the series capacitor is large, it has minimal effect on the frequency of resonant circuit. So next is the snap diode. A pin diode is manufactured like a silicon switching diode with an intrinsic region added between the p and junction layers. This yields a thicker depletion region, the insulating layer at the junction of reverse bias diode. This results in lower capacitance than a reverse bias switching diode. So next is the impact diode. An impact diode is reverse biased above the breakdown voltage. The high doping levels produce a thin depletion region. The resulting high electric field rapidly accelerates carriers, which free other carriers in collisions with the crystal lattice. Holes are swept into the P+ region. Electrons drift toward the N regions. The cascading effect creates an avalanche current, which increases even as voltage across the junction decreases. The pulses of current lag the voltage peak across the junction. A negative resistance effect in conjunction with a resonant circuit produces oscillations at high power levels. So, the resonant circuit in the schematic diagram of the figure is the lump circuit equivalent of a waveguide section where the impact diode is mounted. DC reverse bias is applied through a choke which keeps RF from being lost in the bias supply. This may be a section of waveguide known as a bias. So, next is the gun diode. A gun diode is solely composed of N-type semiconductor. As such, it is not a true diode. So the figure below shows a lightly doped N layer surrounded by heavily doped N+ layers. A voltage applied across the N-type gallium arsenide gun diode creates a strong electric field across the lightly doped N layer. So next is the constant current diode. A constant current diode, also known as current limiting diode or current regulating diode, does exactly what its name implies. It regulates current through it to some maximum level. The constant current diode is a two-terminal version of a JFET. If we try to force more current through a constant current diode than its current regulation point, it simply fights back by dropping more voltage. If we were to build the circuit in this figure below, and plot diode current against diode voltage, we'd get a graph that rises at first and then levels off at the current regulation point as in the figure. So that ends my presentation. I am going to have my talents. I am going to sing Thinking Out Loud by Ed Sheeran. One, two. And darling, I will be loving you till Thank you.